Hello. We've been looking at the magnetic field, and we saw that a moving charged particle will create a magnetic field, and also that a current, which is a lot of moving charged particles, will create a magnetic field. Now what we're going to look at is how a magnetic field affects a charged particle. To get started looking at this, we'll look at several different examples of charged particles in magnetic fields. The first one we'll start with is a positive charged particle that is in a magnetic field, which is indicated, the direction and magnitude of the magnetic field is indicated by this blue arrow, which is showing the vector of the magnetic field at the point where the charged particle is. This charged particle is not moving. Its velocity equals 0. So it's not moving, it's at rest. And what we see is that in this case, the force on the charged particle is 0. So what we can conclude from this is that there is no magnetic force on a charged particle at rest. So a charged particle at rest experiences no magnetic force in a magnetic field. Now let's look at a charged particle that is moving in a magnetic field. So this charged particle has a velocity indicated by the green vector that is parallel to the magnetic field indicated by the blue vector. Again, we see that the force on this particle due to the magnetic field is equal to 0. So we see that there is no magnetic force on a charged particle that is moving parallel to a magnetic field. So if it's moving parallel to the magnetic field, there is no magnetic force. So now let's look at some charged particles that are moving in a magnetic field and are not moving parallel to the magnetic field. In the first image, we see a charged particle that is moving at velocity v, indicated by the green arrow, the green vector, that has an angle alpha different from the magnetic field. And we see that in this case, there is a force, and that force is perpendicular to the plane of V and B. So V and B are in the same plane, and that force is perpendicular to the plane of those two vectors. Now in the second image, we have the same positive charge, and this time the velocity is at a greater angle. So this alpha is greater than the alpha in the first image. So this angle is greater. So in this case, we see that we still have a force that is perpendicular to the plane of B and V, but it is greater. The magnitude of that force, the length of that vector is greater. Now in the third image, we again have our positive charge moving at a velocity v. This time the velocity is perpendicular to the magnetic field. So it's perpendicular. And we see that the force is completely perpendicular to V and B, and that it is even greater. So here the length of the force vector indicating that the force, the magnitude of that force is greater than in the other two scenarios. So we see that the force is greatest at alpha equals 90 degrees when B and V are perpendicular. So bringing these observations together, we see that as the angle alpha between the velocity and the magnetic field increases, the magnetic field also increases. We also see that the force is greatest when the angle is 90 degrees in this example here. And we see that the magnetic force is always perpendicular to the plane containing V and B. So these observations allow us to see that the magnetic force on a charge Q as it moves through a magnetic field B with velocity V must be the cross product. So the F on Q is going to be equal to QV cross B. So it's the cross product of QV cross B. The magnitude of that will be the magnitude of Q times the magnitude of V times the magnitude of B times sine of alpha, which is the angle between V and B. and the direction will be determined by the right-hand rule. So right here in this image right here, using the right hand, we see that if V is your thumb, so the first vector in our cross product, and B is the second vector, because V cross B, that will be our second finger. Then the resultant vector, the cross product itself, will be the force, and that will be our third finger. So we can do the right hand rule, turning our right hand in any direction that we need to get the cross product of V cross B. We can also do what I prefer, which is to take our fingers and point them in the direction of V, then curl them in the direction of B, and now our thumb will point in the direction of F. So again, in this case, alpha is the angle between V and B. Now let's look at a couple examples using our right-hand rules to determine now the magnetic force on a moving charge. Here, first example, we see that the positive charge is moving to the right and that the magnetic field vectors are also to the right. So if we take our right hand and put it to the right and we try to cross it with B, there is no way to cross it because they are completely parallel. And so V cross B in this case will be 0, since the angle between them is 0 degrees and the sign of 0 is 0. So the force in this case will be 0. Now in this case, we have our positive charge moving up. The velocity is moving up. So if we do, and the magnetic field is to the right. So if we take our fingers and point them up and then curl them down to the right, we see that our thumb is now pointing into the screen. And so we see that the force in this case is into the screen or into the page. Now in this example, we have our velocity moving to the right and the magnetic field is into the screen. That's what the X is here, showing us the tail feathers of our arrow. So we do our velocity to the right, curling our fingers into the screen, and now our thumb is pointing up. So the force in this case is up. Now those examples were all positive charges. However, the force is equal to QV cross B. So if we have a negative charge, like we do here in our fourth example, we'll do V cross B and then take the negative of that. So V in this case is to the right, B is into the screen, as we just had in the last example. V is to the right, B is into the screen. The cross product of V cross B is up. However, Q is negative, so it'll be the negative of that, which is down. So in this case, the force will be down. So if we have a negative charged particle, we do V cross B and then take the negative of that to give us the direction of the force. Let's look at what happens. We see that our force is always going to be perpendicular to our velocity. In all of these examples, when we have a force, it is perpendicular to our velocity. So let's look at that. If we have our charge moving in a magnetic field. So here, this figure shows a positive charge moving in a plane that is perpendicular. So it's perpendicular. V is just perpendicular to a uniform magnetic field. So the magnetic field is not changing. So here is our magnetic field. It is into the screen. V is into the page, and it is uniform. Let's look at the first V that we have right here. V is perpendicular to B, completely perpendicular. So in this case, it's moving in this direction. If we take our fingers, put them in the direction of V, and curl them into the page, we see that our thumb points down and to the left. And so that is this is a positive charge. So that will be the direction of the magnetic force on our particle that is moving with a velocity that is perpendicular to our magnetic field. That means that there's an acceleration on this positively charged particle to its left. So it's accelerating to its left. So its velocity, vector will now point more to the left. So the velocity vector will now point more to the left. Now we cross that with B, and now in this case, we see that as it has moved a little bit, the force will now look like that, towards, again, still turning it constantly to the left in this case. So if we follow along, we see that our thumb is always pointing to the left of the motion of the charge in this case. So since F is always perpendicular to V, the charge undergoes uniform circular motion, where the force is pointing towards the center of the circle. This motion is called cyclotron motion. That's what we call it, cyclotron motion of a charged particle in a magnetic field. We can actually visualize cyclotron motion in the lab. Here is an image where we can see electrons undergoing circular cyclotron motion in a magnetic field. So this device has induced a magnetic field. We have a magnetic field. We have electrons inside. You can see they're going in a circular motion, and we can see their path because they collide with a low density gas that then emits light. So let's look a little more closely at this cyclotron motion. So let's consider a particle with mass m and charge q moving with a speed v in a plane that is perpendicular to a uniform magnetic field of strength B. So we know from what we just saw that the force, the magnetic force on Q, will be equal to QV cross B. Now, in this case, we know that that V is in a plane that is perpendicular to the uniform magnetic field. So we can write this as QVB sine of 90 degrees. And the sine of 90 degrees is 1. So this force due to the magnetic field will be QVB. Now, Newton's second law tells us, first of all, that the sum, F net, the sum of all the forces in a certain direction is equal to the mass times the acceleration. So we can write this, in this case, the sum of the forces are just going to be the magnetic force that we found here is QVB, and that will equal the mass times the acceleration. And we know we're going in a circle, so that will be the mass times v squared over r. So we see that F equals QVB equals the mass times the acceleration, radial acceleration, which is equal to mv squared over r. Now we can then solve this for r. And we see that in this case, QVB then equals mv squared over r. So one of those v's can cancel, and I can solve this for r by multiplying both sides by r and dividing by QB. So that lets me know that r equals mv over QB. So we see that the radius of the cyclotron orbit is mv over QB. Now we recall that the frequency of revolution for circular motion is going to be the velocity over the total distance that it's traveling in one period. So that will be 2 pi r. That's the circumference of the circle that it's going around. So in that case, the frequency is going to be v over 2 pi r. If we take what we found here and plug it in for r, we see that the cyclotron frequency would then be F equals V over 2 pi R, where R is mv over QB. So I can cancel one of my V's and bring the QB up on top, and I see that the frequency for cyclotron motion is QB over 2 pi m. Now, if we picture cyclotron motion, right now we've only looked at it being completely in the same plane. So our particle had a velocity that was completely perpendicular to that of our magnetic field. But that's not always the case. So a more general situation where the charged particle's velocity is not exactly perpendicular to B, but has a component that will be parallel to B as well, is shown right here. So we imagine in this case that there is a component, V parallel, that is parallel to the magnetic field. And so the component of V parallel to B is not going to be affected by the magnetic field because V cross B in that case would be 0. So there would be no force acting on the component of V that is parallel to B. So it will continue to have that velocity. That's not going to accelerate. That's not going to change at all. So that velocity will continue. And so the charged particle will spiral around the magnetic field lines in a helical trajectory. So we end up with this helix that we see here, this helical trajectory, as the particle moves along with that same V parallel that it had when it entered the field. The radius of the helix will be determined by V perpendicular, which is the component of V perpendicular to B, and that is what is going to determine the radius of its circular motion. Cyclotrons have been useful for creating instruments as well. The first practical particle accelerator was invented in the 1930s, and that was the cyclotron. In this case, you can see right here, this image of it. We have a bottom magnet down here, and it creates a magnetic field. We see the magnetic field lines coming up. And here is the potential delta V that oscillates at the cyclotron frequency, oscillating the frequency, oscillating the field. And so that will accelerate our particle, it will accelerate our protons. So here's our proton source, and our proton will exit here. So that will accelerate the particles inside the cyclotron. Cyclotrons remain important for many applications of nuclear physics, such as creation of radioisotopes for medicine, even though we use other types of particle accelerators now. Another example of cyclotron motion are the auroras that you see right behind me. So Earth's magnetic field leads particles into the atmosphere near the poles as they come from the solar wind. The solar wind sends these particles, radiative particles, and they get trapped in Earth's magnetic field. And as you see, they go in cyclotron motion. They go in cyclotron motion in these helixes. And as they interact with ions in the atmosphere, they produce the light that we see in the sky. So we've seen that not only do moving electric charges create magnetic fields, but magnetic fields also have a force on a moving electric charge, and that will cause it to move in a cyclotron motion in these helixes that we see.